So the uniform 15 kilogram bar is supported on a horizontal surface at A by a small roller of negligible mass. If the coefficient of kinetic friction between end B and the vertical surface is 0.3, calculate the initial acceleration of end A as the bar is released from rest in the position shown. Alright, so again, first step with this question is drawing the free body diagram and the kinetic diagram. So let's start with the free body one. So we're just going to take out the bar itself. Alright, so forces that are going to be acting on it, well, we're going to have the force due to the wall, contact with the wall. So let's call this one NB, and we're told that we have friction acting against the wall here. So I'm going to assume that this thing is going to try and fall down, so this point's going to slide downwards. Friction then opposes it, so it's going to be upwards. So that's the friction at point B, and we know it's equal to the kinetic friction coefficient multiplied by the normal force at that point. We also know that we're going to have weight in our diagram. That's because we're looking at this thing falling in the vertical plane, and we can say it's going to act through the center of gravity, which should sit at the center of the bar. So that's going to be mg. And finally, this point here is in contact with the ground again, so it's going to have a normal force acting through it. This time we're not considering friction at this point, so that's why, yeah, we're not going to put it in. So now we need the kinetic diagram. Alright, so we need to, I guess, first of all think about whether this thing is going to rotate, and I think it is. I think this point's going to slip this way, this point's going to slip down, so we're going to get clockwise rotation. So that's going to be the direction of alpha, and of course this is about the center of gravity G. We're also going to end up with the center of gravity of this bar moving, which means that we're going to have some translational acceleration that we need to draw in. So I'm going to say that we're going to have a y component that's going to move the bar down, and it's going to have an x component back to the left. Okay. If you get any of these directions wrong, it shouldn't matter. It should fall out in the maths as being a negative value, and you'll flip it over in the other direction. So we have three governing equations that we can apply. I'm going to start off with the one in the x direction. So, using our regular xy coordinate system, in the x direction the only force that we're going to have is NB. And it's in the negative direction, so it gets a negative value. From the kinetic diagram, we can see that we have acceleration in the x direction, and I've assumed it going back to the left. So it's also going to be negative. And what that's going to mean is we can say that the normal force at point B is equal to the mass, and we were told it up the top, the mass was 15 kilograms, multiplied by whatever the acceleration in the x direction is. So I'm going to set this up to solve with a matrix method at the end. So if I make this NB minus 15AX bar is equal to 0, that's going to help me later on. So that's going to be equation 1. Alright, so let's apply our next governing equation, which is looking at the y direction. So we have a few things going on this time. So we're going to have NA going up, mg going down, plus the force of friction, which we've simplified to this, going up. And it's equal to, this is the only component that we have in the y direction, it's going down, so it's going to be negative may. Alright, so substituting some numbers in, again I'm going to try and rearrange it as well to solve with the matrix method for the simultaneous equations. So Na we don't know. We know that the mass was 15. We know that friction was 0.3. And again, the mass was 15. So if you want, you can rearrange this. And I put all of the different unknowns on the left-hand side and the constants on the right. So that becomes equation 2. Alright, so we now can use our third simultaneous equation, our third governing equation, and that's to sum moments. So we can pick any point that we kind of want to sum about. I think I'm going to pick to sum about point G, but again, it's up to you. It should work if you pick another arbitrary point as well. So summing moments about point G, we know that it's equal to I bar alpha, and we're going to consider anti-clockwise as the positive direction. So, summing moments about G, first one I guess we consider is NA. Scroll this up a little bit. And the distance that's going to occur between NA and MG, we should be able to get from our diagram. This is a 40-degree angle in here. We know it's 2.4 meters, so that makes each side of this 1.2. So the distance that sits in here, this horizontal part, is going to be the sine component. So 1.2 sine 40. Okay, we also need to think about the direction. So this is going to try and push us it's clockwise about point G, so it's going to be negative. Alright, so let's now consider NB. So it's going to be multiplied by the distance that sits in here, which is going to be the cos component. So 1.2 cos 40. It's going to try and push us anti-clockwise, so it's going to be positive. And finally we have the friction force, which is mu k times NB, and the direction in here is the sine component again. So it's going to be 1.2 sine 40. Direction will be anti-clockwise, so positive. So for the right hand side, we know that it's equal to I bar alpha, and it's a thin rod. We want to calculate it about the center of gravity. So if you look it up in a table, the general form of the equation for I bar, in this case, becomes 1 on 12 ml squared. So we can work it out. Mass we said was 15, and the total length of the bar is 2.4 meters. So this works out to be 7.2 kilograms meters squared. So that's what we can substitute in for I bar. And alpha, if we go back to our diagram, we've drawn it in the clockwise direction, so it should go in as a negative value. Alright, so again we can substitute in a bunch of different unknowns that we've been given and simplify down some of these values as well. So our equation becomes this. I think I've swapped these around, but anyway. So if we put it all together on one side of the equation, we end up with this. Okay, so we've got 3 simultaneous equations, but if we count up the unknowns, I think we're going to have too many to be able to solve at this point. So we have NB, NA, AX, AY from these ones, and then down here we've also got alpha. So we've got 5 unknowns. So 3 equations, 5 unknowns, you're not able to solve directly. So what we need to do is look for other relationships that we can develop in order to get at least 2 more equations to solve with. So for these ones where you've got constrained motion, it's really not that bad because we know that the relationship between the acceleration of this endpoint and this endpoint are restricted, and also point G is on that bar as well. So we're going to be able to use that to derive a couple of extra equations. Alright, so we're going to relate together, first of all, the acceleration of A and B. Okay? So we know that the acceleration of A relative to B is equal to the absolute acceleration of A minus the absolute acceleration of B. Okay, and both of these points are on the bar, so we know that they're related to each other. So let's go through and fill out the equation. So the acceleration of A relative to B is going to have both a normal and a tangential component. So the normal component is going to be omega cross r, and the tangential component is going to be alpha cross r. Okay, let me just draw a small diagram over here. So this one up here is point B, this is point A. We know that this whole thing is rotating. Alright, so yeah, that's what we're trying to relate together. Alright, so in this equation, we know that this bar up here told us it was kind of released from rest somewhere. Alright. So right here, released from rest. So if it's released from rest, that means it's going to have no angular velocity at that instant because it's at rest. So we can say that omega then for the bar is equal to 0, and we drop the normal component of the equation. So all that we're left with is the tangential part, and we've said that alpha is in this direction, which is clockwise. So let's call this negative alpha k. And the radius in this equation is relating together A and B. So if we use our regular xy coordinate system, as we have been doing, we're trying to relate together A from B. So we start at B and measure back to A, so it's going to be this way. So it's going to be negative in the y direction. Remember the length was 2.4 and the angle was 40 degrees in here. So it's going to be 2.4 cos 40 j, sorry. And then this component is going to be negative 2.4 sine 40 I. So if you multiply this out, it becomes that. Okay, so that solves the first term in this equation. Now we just need to look at the other two. So for the acceleration of point A, what we're assuming is, well, I'm going to assume that this one was falling down and this one was going to the right. So the acceleration of point B is downward and the acceleration of A is to the left. So in vector form, I can write this as AAI. It's only got an x component. For B, very similar, it's going to be negative ABJ because it's going down in the y direction. So we can write this equation with everything substituted back in. Sorry. So it's going to be a double negative in there. So if we take out our I and j components separately, we find that the acceleration of A is equal to that in terms of alpha, and for j, same kind of thing. You're going to get that the acceleration of B is equal to 1.543 times alpha. Alright, so remember that we're trying to get some extra equations that relate together these variables in here. And at the moment we haven't really done that because we just ended up with the acceleration of A and the acceleration of point B in terms of alpha. So if we use these, it's just going to add more unknowns into the mix. However, what we are going to be able to do is we know that point G is also on this bar and it's going to be rotating at the same rate. So what we can do is either relate together the acceleration of A and G or B and G, and we should end up with an equation that includes these last three unknowns. So let's go ahead and do that. So it doesn't matter which one you pick in terms of A or B. I'm just going to pick that we relate together A and G though. So let's go ahead and kind of do the same thing as we did before. So the acceleration of A relative to G, again it's on the same bar, so it's going to have that normal and tangential component. And if we write them out, it looks like that. Oops. Alright, so we can kind of go through the same process where we know that the omega in this equation is the angular velocity of the bar, and it's going to be 0 at the beginning because it was at rest. So we drop this. All that we're left with is alpha crossed with r. So alpha is going to be exactly the same as it was before, because points A and G, they're still on this bar. Okay, so it's going to be alpha k, and we assumed it was going clockwise, so it's going to be negative. And r in this equation this time is relating together A and G, so it's going to be A relative to G. So if we scroll back up, we need to start at G and measure back to A. So it's going to have this component in Y and this component in X. It's basically going to be half of what we had before. So it's going to be 1.2 in both of these places. Okay, multiplying this out, you end up with an equation. Like that. Alright, so 2 terms left in here. So the acceleration of point A we worked out, okay, and that's why we went to the effort of doing that previous step. So we now know acceleration of A in terms of alpha is that, and in vector form we said it was equal to negative I, because it could only move in the negative x direction. So now we just need to look at the point G, and this is the one we're kind of interested in. So we know the acceleration at point G is going to have an x and a y component, okay, because this point here can like move in space in both x and y. It's going to form an arc. And if we scroll all the way back up, we said it's going to move in the negative x direction and negative y direction as well. So let's put this in terms of x and y components. So I'm going to say it's moving in the negative x direction at the rate ax bar, and in the negative y direction at the rate ay bar. So I should be able to now work out these from subbing back into this equation. Okay, so the only unknowns are these two right here, and we just need to solve for them by taking out the x and the y components separately. So if I start with I, so ax bar ends up being equal to just 0.92 times alpha, and j's we end up with that. So if we want to use the matrix method for each of these, we just need to rearrange them. So this one would become that when we chuck everything on one side, and this one would become this. So we can treat these as equation 4 and equation 5 of our simultaneous equations, and we can see that we are only relating together ax alpha, ay alpha, and if we go back to where we had our list of simultaneous equations, they were in the list. So basically now we've added 2 equations in here, so we have 5 equations, 5 unknowns, and you should be able to solve. So if you go ahead and use the matrix method, alright, this is the equation. So X is your a matrix of unknowns. So these are all the ones we have. A is the matrix of the coefficients in front of each of these unknowns across all 5 of our equations. So I'm just going to go through and write them out. Okay, that matrix gets inverted, and B is the matrix of constants on the other side of the equation. So only one of them actually had a constant. So let's write it out here. If you go ahead and solve, these are the numbers that you end up getting. Alright, so the only one that you were kind of asked for in this question is what alpha is. So that corresponds to the third one in the equation. So we ended up with alpha is equal to 3.22. We did everything in the normal base units, so this would be in radians per second squared. And since it came out positive, the direction that we assumed is correct. So we assume this to be in the clockwise direction. So that's going to be our answer. So I guess the moral of this one is it's quite an involved question, simply because you needed to develop the extra kind of 2 equations that didn't fall out of your governing equations. So this is usually only going to be the case where you have some very specific constrained motion. If you have a more simpler scenario, you should be able to get whatever unknowns you need just out of using your 3 governing equations. So that's all I've got for that one. See you later.